Do you know how on Twitter a person will ask a question and end the tweet with, "I'm trying to see something," and it feels like they're trying to confirm a belief that they have? Well, I'm trying to see something. Before continuing this video, pause and go back to your textbook and just read the section on the Born-Haber cycle. Then come back and I'll let you show how my colleague taught me recently. Hi, welcome back. So I suspect the way that my colleague taught me is probably a really good way to teach the Haber cycle to get lattice energy. I've I've read the textbook many times and I see the same diagrams over and over again, and it never really clicks with me until my colleague taught me this way. So before we get to the setup of the Born-Haber cycle, let me describe what it's about. Born-Haber cycle. Okay. It's the use of Hess's law to string together a series of reaction steps to calculate the lattice energy of an ionic solid. Lattice energy of an ionic solid. Okay, and then lattice energy, we've seen it before as a ELAT, but also it's the same as delta H naught LE, lattice energy, the enthalpy at standard conditions. Don't worry, I'll show you what lattice energy is next. We've forgotten. Lattice energy equals amount of energy. Okay, so it's positive to convert a mole of ionic solid into its component ions or constituent ions in their gas phase. For instance, the delta H of this reaction is going to be the lattice energy. NaCl solid going to sodium plus gas plus Cl minus gas. And here EA, no not EA, ELAT, same as delta H naught LE, is positive. Don't forget that. Because there's a warning. Some textbooks say the lattice energy is the reverse reaction, and it's negative. ELAT of the formation of NaCl, of the ionic salt, as the reverse, which is the formation of ionic solid. Now, the fact of the matter is, lattice energy cannot be measured directly. We'll have to use this Born-Haber cycle, which has a Hess's law approach. So again, let's change it to delta H LE is not measured directly. We're going to use a Hess's law approach. Okay, so we're going to have a list of reactions that, when added up, will give us this. And that's called the approach is called the Born-Haber cycle. So ultimately, this is the target. If, for instance, sodium chloride is the salt, the ionic solid we are trying to figure out the lattice energy for. Okay. Let me show you now what my friend taught me, how he described the Born-Haber cycle. And we are going to use a totally new sheet because I want to get all of this onto one page. Okay. Our target is this. The enthalpy change, or the delta H of NaCl solid going to its constituent ions in their gas phases. And this is the question mark delta H Le, or lattice energy, and we expect this to be positive. Wait, do we expect it? Yeah, we expect it to be positive. Okay, where do we start? We're going to start with something that we know, which is the delta H of formation for NaCl. The thing I'm going to do is I'm going to label the steps or the reactions of the Born-Haber cycle for sodium chloride using numbers. 1. I know there are 5 steps for sodium chloride. For a different ionic solid, it may be different. So this is not something that you should memorize, but I just want to space this out because I want to take also, or I want to give you some notes below. So we have the target reaction. You'll see what I'm getting at in just a bit. And here I'm going to put notes for each step. Okay. Number 1, the first reaction is this. NaCl solid. Okay, so we got that on the reactant side. So when we add it up, we should have most likely NaCl solid on the left. I don't know this delta H, but I can get to this delta H. And can you tell me where this is coming from? 1/2 Cl2 gas. The delta H for this process equals 410.9 kilojoules per mole. Let me give you a hint. These are the element constituents of sodium chloride, not in their gaseous state, but in their standard state. Right? Chlorine gas, or chlorine, the element in the standard state is Cl2 gas. Sodium is sodium solid. You know what this is? This is the reverse of the heat of formation for NaCl, right? Have these components to make 1 mole of NaCl. So in my notes, I'm going to say this is the reverse of the delta H of formation of NaCl solid. Okay, this is from the table, not this reaction, but the reverse reaction. And it's negative on that table. So this quantity is from a table, and it's going to be negative. Right? The formation of the ionic solid is negative exothermic, going in the left direction. So when we take the reverse of that number that we see on the table, that negative will become positive. So this is the reverse of the heat of formation for sodium chloride. All right. Next, we're going to let's start with sodium. Step number 2, we're going to take the sodium solid. Okay, see, this is setting up to be Hess, right? Because when we add these up, these two are going to cancel out. So we're going to slowly walk our way from sodium solid to sodium positive gaseous. That is the trick. Same thing with chloride. But anyway, how do we get closer? Well, let's make sodium, let's not make the ion yet. Let's make it gaseous, Na gas. Well, what is this? This is the standard state of sodium, and we're changing it to gas. So this is the heat of formation for sodium gas. Okay, so again, number 2. Just remember, if you have a reaction where you see the element in its standard state, you can manipulate that reaction to get a heat of formation. But this is now the heat of formation, not the reverse, right? Because we are starting with the standard state of Na gas. So again, we were getting this from table of the heats of formation. Okay, easy enough. It's really, is it really a preference? Instead of going ahead and changing this into ion, let me take care of the chlorine. Oh, sorry, this chlorine right here, and get it into 1 atom of chlorine. We're going to take this 1/2 Cl2 gas. Okay, so that is the standard state of chlorine going to just 1 atom of chlorine gas. So again, we're starting with the standard state. Forget about the coefficient for now. Okay, we're starting with the standard state for chlorine, and we're changing it, right? Because the standard state of chlorine is diatomic, and we're changing it to a different form of chlorine, so that will have a non-zero enthalpy of formation as well. This is delta H of formation of now Cl gas. See, both sodium gas and chlorine gas, those are not the standard state of those two elements. And this is from the table as well. And yes, I realize I have forgotten to write the delta H's. So the delta H for this process is positive 107.7. And then for this process here, to get chlorine, a single atom of chlorine gas, 121.7. Okay. So far, everything has been endothermic. Okay, everything has been endothermic, and I'm just trying to figure out, would you be able to tell that just from the reaction that we have to add heat for each of these reactions to occur? All right, so now we're here. We got to get to here. All right, let's go back to sodium, and let's make it an ion. Okay, so we're almost there. Na gas. We want to make the ion, so what is that? We have Na plus gas plus electron. Does that look familiar? We are ejecting an electron. Let me give you the energy first, and then we'll explain it. Okay, 495.9. So it requires energy. This is the energy required to ionize sodium gas. This is an ionization energy, right? Ionization energy is the amount of energy needed to ionize an element in its gas state. And it's the first ionization energy because we kicked out an electron from its neutral state. Maybe you'll recognize this. This will jog your memory. IE1, the first ionization energy. And this is for Na. And again, remember that these are measured, ionization energies are measured in the gas phase. So this is perfect. Gas phase. Now I know we are ionizing chlorine to chlorine minus, this chlorine. But that's not ionization energy, right? Ionization energy is to lose an electron to become positive. What is it to gain an electron? Because if we could name this process, we have a shot at looking at the right table for these delta H's or these energies. This chlorine gains an electron. So chlorine is on the right side of the periodic table. Those are very electronegative atoms. Okay, the halogens, not the noble gases, but the halogens are very electronegative. This number, our first negative, 349, that is an electron affinity. I know it's been a while, but if you think back, ionization energy is the energy required to kick out an electron. So its energy is positive, its delta H is positive. To lose an electron actually is exothermic. It actually releases energy when you release, when you add an electron. When you add an electron, it's exothermic. Okay. Let me give you those notes. Number 5, this is EA. Does that look familiar? This is electron affinity. And again, it's measured from the gaseous state, but it equals the energy released. Okay, so I think maybe what I'm trying to say is that when you read it off of a table, it's telling you the energy released, the amount, the positive amount, but since it is released, we are going to say that the delta H, it will result in a delta H that's negative, right? Releases energy or releases heat. That is actually our only negative delta H. Okay. Well, if we add them all up, I want to leave this clean, but normally with Hess's law problem, you will start canceling out things that are happening on both sides. But look, sodium, solid, okay? 1/2 chlorine, Cl2 gas, 1/2 Cl2 gas. And you could go down the line. Eventually, you'll have NaCl when you add everything and cancel out the components on both sides. You'll have sodium chloride going to, give me 1 second, that's not canceled out, and that's not canceled out. Okay. Even the electrons, right, cancel out. But anyway, Na plus gas, Cl minus gas. That is the equation for lattice energy, because we defined it, this textbook defines it as the amount of energy to convert a mole of ionic solid into its constituent or component ions. So according to textbook, this is describing lattice energy. The energy associated with this process is lattice energy. I'm only emphasizing that because, again, some textbooks have the lattice energy as negative because they're going in the opposite direction, right? Because by combining these two to make a bond, an ionic bond, it actually releases energy. But in this textbook that I'm using, is going to be defined as the energy needed to break up the bond. So that requires energy. Okay. Oh, I never calculated it. Let me do this real quick. Check my math. Is it going to be negative or positive? Well, it requires energy. Lattice energy, for our case, will always be positive. 787. We'll give it one place past the decimal. Put your units, and even put what it is specifically. Okay. So again, the idea is that lattice energy, this process, cannot be measured directly, but we could go through a pathway to get to this equation via Hess's law using what's called the Born-Haber process. Yeah, remember, enthalpy is a state function, so it doesn't matter if you take many steps or if you take few steps, as long as the initial and the final are set, then the delta H should be always consistent. Okay, let me talk for another 2 or 3 minutes, because I want to warn you that while this may seem, I don't know, fairly digestible, okay, and actually it's kind of short, you can't, shouldn't memorize this, because this is very specific for sodium chloride. Okay, I'm going to give you an example where we're not going to have 5 steps, or likely we're not going to have 5 steps. But before I do that, isn't this, I think it's much easier than what I read in the textbook. The textbook, if it's anything like the one I'm using, shows a Born-Haber as like a diagram with arrows going up, and then this arrow going down, and then the difference being the lattice energy. And for me, the signs I get really confused about the signs. I'd rather just think about this and understand these notes to predict the sign, or to make sure that the sign is proper, like it was something that I expect. Okay, 5 steps. Warning. It's not always these steps, and it's not always 5 steps. Both of these ions are going to the 1, +1 or -1. Lose electron or gain 1 electron. But what about if we have MgO? And we want to figure out the delta H lattice energy. Well, think about what we need to get through. We got to, break this up into its constituents at its standard state, because I think we can always start, it's good to always start at the heat of formation, or the reverse of the heat of formation. So let's mark this as a starting point, actually. Starting point. This is the reverse of the delta H of formation of the solid. Okay. Always have that as a starting point, and then you're off and running, because you got to get these now individual elements into its gaseous ions. So start there. But anyway, okay, fine. We start with the formation of MgO, the reverse of the formation of MgO, but eventually we need to ionize magnesium gas, and we specifically need this Mg plus gas plus an electron. You know what that is? Again, we're kicking out an ion, kicking out an electron, So this is the ionization energy, IE1. But MgO, the ion is 2 plus. So we actually need also, we take that ion we just made and we kick out another electron. That's what we need. And then we could use this in the final step to get the lattice energy. So that analogously is that cation in the gaseous state. Okay, so what's that? We actually have to look up the second ionization energy, IE2. Okay, so that's one reason why this would not have 5 steps, because we have this extra step, and actually for oxygen, we will have a second electron affinity step. But also, just be aware or be ready for a twist. We have an equation here, right? X plus Y plus Z, etc. gives me my target. But this last equation, the result doesn't have to be the unknown. Any one of these steps could be the unknown. Okay? So, for instance, what if they give you delta HLE of MgO? And then they ask what? They could ask, for instance, the electron affinity, the second electron affinity for oxygen. And so by the time you're ready to gain another electron, you're going to start with oxygen minus in the gas state. Whoops. And then plus 1 electron, right? Adding electron is electron affinity. Goes to O2 minus gas. Do you see that? Okay, good. So that's another twist. Your unknown X doesn't have to be the lattice energy. It could be any one of these. It could be the heat of formation for the element. It could be what is it? This is the ionization energy. It could be the electron affinity. Okay, the professor could cover up any one of these numbers. You just have to be able to draw the steps so you know how to solve for that unknown, right? How to solve for that unknown. Okay. I will let you be, but what you could do to practice is, why don't you write the steps? The individual reaction that, when added up, could give us this lattice energy, the lattice energy for this reaction. MgO, can you predict what I'm going to write? Lattice energy, break it up into its ions into their gaseous state. Mg2 plus gas plus O2 minus gas. Okay. I may actually do the full problem, maybe this one, where they give us the lattice energy and we have to solve for the EA2, electron affinity. I may be able to do this in another video, probably right before we review for as a review for the exam. Oof. Okay. Good luck. Actually, this is the end of Unit 1, at least the lecture portion. Again, if we do more review or if I decide to do a lot of different problems, those videos, if they're related to Unit 1, will be obviously placed in Unit 1.